So now we're doing Lagrange multipliers. The idea of Lagrange multipliers is that it allows us to include terms in Q, our generalized coordinate, that are not independent. You know, i.e., if n is the number of elements in Q is the size of Q, and m is your degrees of freedom, n can be greater than m. Up till now, we've assumed that the number of coordinates and number of degrees of freedom are equal, which implies, as long as that fully spans the mobility space, that implies your coordinates are independent. And the way we did it was, I mentioned that we tend to relax the constraints. So if we start off,
Are you recording?
Yes, thank you. So where we left off before was we had Lagrange equations, which recall were for I equal, or the sum for j equal 1 to n, and I'm just writing Lagrange again, but it's good to do it. That's what this class is, so you'll never forget it. Partial, or the DDT of the partial of L with respect to Q dot minus the partial of L with respect to Q. We can say equals Q cap Qj, or here I'm going to say minus Qj. This whole thing times the virtual Qj equals 0. So before, when these are independent, we could say that equals 0. And you had that in your notes. I just lost my notes from Tuesday. You had that in your notes. Before, we said those were each independent. Now they're not. And by now, I mean, i.e., n is greater than m. You have more coordinates and degrees of freedom. So here's what you do. You write your constraints. So your steps are, I'll write them out. 1, write constraints. And over here, I'll work an example that I started. So for example, let's say z equals 0, I think is the example I used. And I had x squared plus y squared equals L squared. You could have others. You write your constraints. Step 2, now, and those are the constraints. Z is 0. That's the z value never changes. It's always 0. X squared plus y squared equals L squared. With L, this constant term. The second step is that you want to take the differential of the constraints. And when you take the differential of constraints, they're going to be in a differential form. So that would be something like over here, like dz equals 0, and 2x dx plus 2y dy equals 0. That would be an example of the differential form. And then I'm going to say 2.5, write in a more compact form. And the reason I say this is how you always see it. So we're going to write our constraints as follows. So we're going to write them like this. The sum of a kj dqj. Actually, if you're writing it kind of the same way I am, let's write this form over here, and then we'll put our example on the right. Sum a kj dqj, and here we're summing over j for j equal 1 to little n, plus, if you have any time derivative terms, then you'll get those bk dt equals 0. And this is for k equal 1 to L, and L is the number of constraints. So let's do that over here. Okay, on our example, we're going to Turn that thing off. On our example, we're going to, right. On our example, we're going to get, sorry guys. This is going to be our A. So it looks like we've got dz, dx, or maybe I'll write it out, dx, dy, dz terms. Let me get this one first. So the first constraint says 1 times dz equals 0, and there's no b term. So I'll just write down 0 for the b term. I'm really squeezing it in there, sorry. The second constraint says 2x times dx plus 2y times dy plus 0 times dz plus 0 times dt equals 0. Can you read that? Yeah, does that work? Kevin's giving me that barely look. Ah, yeah, where A and B are from the summation, okay? You know, when you see, sometimes people call this tensor notation, that I could drop the sum and then there's some rules. I don't really do it much, but if you see the sub notation, the 2 subscript to imply is the two-dimensional array. 1 subscript means a one-dimensional array, 3 subscripts, 3-dimensional array, and so on. So whenever I see that, I say, oh, that thing. Yes. Okay. Yeah, I ran out of space for my. That's the BK term. That's the BK term. There's a little more room. That's the BK. So this would be, you know, this little term here, if you care, would be, now it depends on the order you wrote the dx, dy, dz. You've got to choose that. But this would be my A, you know, k equal, A row 1, column 1, you know, it's where it's constraint 1. Here, let's expand that. That's A row 2, column 1. So it's constraint 2. And it's generalized, it's the generalized coordinate term number 1. Okay. And then the b's are 0. The b's actually going to see in a moment go away. So next we write, so that was differential form. Now we write in variational form. And the idea of a variational form is everything happens contemporaneously, you know, everything, all the motion somehow occurs at the same time, which means time doesn't change, which means you simply drop the b. The b goes away. So you get the sum for j equal 1 to n, a k sub j, t, not d, but virtual qj. And Lagrange is a virtual method equals 0. So over here, we just get that a from before times dx, dy, dz equals 0. Okay, so you write in variational form. And then the last step. Include the constraints in variational form. Your matrix equation. Yep. Let's go dx dy. Ethan, you're good. You're very good. It should be our delta. That should be our variational form. Thank you. That was important for me. Good call. Good call. Okay, so step 4, include the constraints in variational form. This is a compound sentence here. Times the Lagrange multipliers. And our Lagrange multipliers were the lambdas. Lambda k, 1 for each constraint. It's more of a run-on sentence. So include the constraints multiplied by the Lagrange multipliers into Lagrange's equations. And here's how it goes. You get the sum for j equal 1 to little n, d dt, partial Lagrangian with respect to qj dot, minus partial Lagrangian with respect to qj, minus q, cap q sub j, all right, times variational qj equals 0. That's what we had before. So now, right here, I've left a nice spot to include the constraint multiplier by the Lagrange multiplier, and it goes exactly this way. I'm going to put a, let me come back and talk about the sign. I'm putting a minus at the moment. So the sum for k equal 1 to L, lambda sub k, a, k, j. All right, so see this? We have the variational form. We have the a, k, j. Actually, you can see the whole constraints there, right? You just take the lambda, you multiply a lambda times each constraint. So you have a lambda on this row, a lambda times this row. So it gives us lambda k times a, k, j times delta, the variational qj. I pulled it out. So just get this term. And now these are independent because of the lambdas, right? That was the whole idea. And so we simply write Lagrange's equations this way. The ddt, the partial of Lagrange with respect to qj dot, minus the partial of Lagrange with respect to qj, minus cap qj, minus this sum for k equal 1 to L, lambda k, a, k, j equals 0. We do that for all j. So so we just get Lagrange from before, plus this one extra term, the lambda times the. Let me say 2 quick words about it. One is the sign. Remember, I think of it as the Q's are the generalized force. The force is on the right-hand side. You know, it's like think F equals NA. This type of the form of equation you're ultimately getting. Only getting generalized stuff. So actually, so the Q's would be on the right hand positive, and then the lambdas are forces and force constraints. That's how I think of this for what I'm quoting. Hence the negative. And I get one of these guys for each thing. So if I look at my matrix, what I'm getting for each equation, I'm basically getting, you know, for, in this case, I have 3 generalized coordinates, right? This is my Q. So when I, you know, so when I'm doing Lagrange, I'm going to say, okay, well, let Q equal X. they'll say like q equal y. Then they'll say like q equals z, right? And so what I do for each equation, I take the first row times lambda. So when q equals x, I'm going to take 0 times lambda 1 plus 2x times lambda 2. I have two constraints to two lambdas. So when I go to q equals x, I'll take 0 times lambda 1 plus 2x times lambda 2. Then when q is y, I'll have 0 times lambda 1 plus 2y. That's how it is. So it's each column gets multiplied by multipliers for each. Example is the best way to show this. Any questions on that? Oh, yeah. Yep, I'm gonna let you get that up. Yeah. Good question. I don't think you have to worry about the frames on this. And the constraints can be holonomic or non-holonomic. Let me say this. A lot of times you'll see all the times Lagrange only applies to holonomic systems. Lagrange doesn't handle non-holonomics. Well, that is true up until this point. If you have non-holonomic, these other ones, and these are any type of wheel rolling class. This is how Lagrange can now handle it. So in terms of the type of constraint, I think it can handle any. And in terms of the frame, I don't think it matters. Now, let me say this. Remember, let's say our constraints are F. This is an aside. I'm going to do an aside for just a moment. Say our constraints, we've kind of been using this F. So it's F, Q, and time, right? That was the old form of the constraints. Here, these are holonomic. So, what would such a constraint be? Let's say, I've got these two masses, M1 and M2, that are constrained by some constant length. I would just say that the length here is constant. So it'd be something like x2 minus x1 quantity squared plus y2 minus y1 quantity squared equals L squared. If I was using generalized coordinates, x, x1, x and y for each, okay? So that would be example. Look, this is only a function of the x's. Let's think about now a non-holonomic constraint is one you can't write just in terms of q and time. So it'd be in terms of q dot, and time. And the classic one for a wheel, if you think about a wheel rolling or a differential, a robot, a differential steer robot, for example, kind of the most simple one. Here, you say that the it's kind of a bad picture, but I can say that the velocity at the center of that wheel, so let me say that's the right wheel, the velocity at the center of the wheel is equal to the angular velocity of that wheel, I'll call it theta right dot times L, or the R, let's call it R radius, okay, that's pretty straightforward. But I can't make any statement on what the position of the robot is, okay? So here's a constraint. So if I'm using perhaps VR as a generalized coordinate term and theta LR, or maybe, right, my constraint here is written in velocity form. It's got this theta dot term, and I can't integrate that back. There's no way to integrate back and get, my classic examples. I couldn't go out and put odometers on Tommy's wheels of his car or truck they drove here, and then go look at them the next morning and tell him where he's been, right? I can't deconstruct that. Anyhow. So, Douglas, when I think about it this way, when I think about those two, I'm writing it in terms of the generalized coordinates. I suppose I think I could write the constraint in any frame. Somehow frames don't seem to, I don't think that would be a problem, as long as it's consistent, as long as I've written the constraint properly. Good, other questions? Other questions? All right, examples. We have two examples to do before Drew comes up here. Rips this pen out of my hand. All right, example one. The first example is going to be easy. The second one is kind of, well, they're both pretty easy. Got a big example of time. All right, so I'm doing this most simple pendulum. We looked at it, but the nice thing is it's going to let us work out the parts and you can see where things go. So here I have a pendulum, length L, mass M. I think I'm treating it just like before. So I got N1, N2, B1, B2, and I want to use the generalized coordinate set Q. So I guess what I've been saying, step 0. Let's let Q be theta and L. All right. So my N is 2, but it's one degree of freedom. My M is 1. That implies there has to be, I mean, I'm assuming a rigid length L. Okay. So that means I have to have one constraint. So therefore, one constraint. And that means K is 1. And in this case, what's my constraint in this case? Let's think about this one. And I want to write a constraint in terms of those generalized coordinates. So I chose theta and L as my generalized coordinates. What would be the constraint? And it's a rigid length pendulum. It's just a plain old pendulum. Rigid length pendulum. Generalized coordinates are theta and L. L is constant. Yeah. So L is some constant. Yeah. I'd kind of like to write L equals L, but that seems a little odd. So I'll just write L is constant, some constant. Okay. Now that's in terms. I mean, well, let's call it L is LC as a constant. Okay. So here in Q, I treat it as a variable, right? It's a generalized, it's a coordinate, implying it's going to describe my system, and I expect my system to move. The constraint says, hey, guess what? The derivatives are 0. But here I can write this one in the holonomic form, right? L is, it's just here in terms of. Okay, so let's carry on with Lagrange. So step 1, I name a T. It's going to be, just 1/2 M I VG vector dot over VG. Here, it's a particle. I'm treating it as a particle, so I don't have that 1/2 omega dot I omega term. And my V is going to be, looks like that's going to be negative MGLC theta. My VG is, what's my VG? Well, my VG is going to be the dt of R. My R is negative LB2. And my, I guess I need my angular velocity. My angular velocity is going to be theta dot in the B3. So when I take that derivative, I get, look, L is a variable, right? So I'm going to get negative L dot in the B2 plus, and I'm doing this one quickly. Stop me. So I take the derivative of this guy. Now L is the generalized coordinate. So I use my L dot term. And then I take the angular velocity here across this axis. So 3 plus 2, that's a negative 1. So it's a negative times negative or positive L theta dot B1. That's my velocity. Put that back into my T. So my T is 1/2 M L squared theta dot squared plus L dot squared. Next, I get my components. So I'm going to have Q equals theta and Q equals L. Q equals theta, I get the partial T with respect to, that's a theta, not a 0. Theta, it looks like T is 0, thank you. That's nice. Partial of T with respect to theta dot, that gives me M L squared theta dot, and then the ddt of that thing is just ML squared. Oh, no, I've got to be careful. I'll write that out. The ddt of the partial T with respect to theta dot is ML squared theta double dot plus 2ML L dot theta dot. Got to keep in mind, I've got to take, all the generalized coordinate terms to show up there. My Q sub theta equals 0 because I don't have any other forces. And I'll come back to my, probably going to stick it in above. So I'm going to come back to my, it might not hurt to write my constraint terms here, but I'll come back to that. Now, Q equals L. I need the, oh, I did forget a term, didn't I? I need the partial of V with respect to theta. So that's just going to be positive MGL S theta. Now I take the derivative with respect to L. I get the partial of T with respect to L. So it looks like I get M L theta dot squared. I need the partial T with respect to L dot, which is M L dot, and then the ddt of that thing is M L double dot. My Q sub L equals 0, cap Q sub L, and the partial of V with respect to L is, looks like it's going to be minus mg cos theta. I think I did that right. Okay, so it's Lagrange as before. What's odd right now is you keep thinking, well, L's a constant, L's a constant. But it's not, it's one of our generalized coordinate terms, so treat it as a variable. All right, up above, I wanted to do this up above. Let's do our constraint. I'm going to do it above so I can include it in the Q equal theta and Q equal L terms, so when I add them up, it'll be easy. So our constraint, so what were our steps? First step, we said write the constraint, so now it's L equals LC, a constant. Then we said, what did we say to do next? Now, what did we say to do next? What was step 2? Differential. Okay. So I need to differential this thing. So I guess in a way I'm taking the gradient. So I take the partial with respect to L. So it's going to be 1 times dl plus 0 times d theta, because I got to take it with respect to all my terms. Do you see that? Well, we're in the added step. We're in the Lagrange. Yeah, we can call it 2. Yeah, this is a 2.5. So, you know, honestly, Kevin, thinking about it, what would have been nice is to, I actually moved it above because I want to insert it before, well, Kevin, I would like to have down here list what's my lambda sub k, AKJ. I want to list that term. Do you see what I'm getting at? And over here, I want to have my A, lambda K, A, K, L. So I can add them up. So I guess, I guess it is a step 2.5 that comes right before step 2. Maybe it should be a step 1.5. It's an additional step. What do I do? I don't know. Okay, you decide. You'll reconstruct. I can see Kevin. You know, at night crossing out. That's not right. Which he's half the time he's right. Okay. So anyhow, I'm taking the differential of my constraint. So I get 1 times dl plus 0 times d theta equals the d. You know, I'm taking the differential of the LC constant, which is 0. Okay. That's the differential form. If I were to just quickly, jump ahead to variational form, I could rewrite it. The variational form, I would just drop the time, right? So it'd be 1 variation of L plus 0 del theta equals 0. And then finally, I can write it as my matrix. So it looks like I just get a 1 row by 2 columns. I'm going to do theta first, then L. And so it's 0 times del theta plus 1 times virtual L, okay? So the first term, so here I have, notice my K is 1, or my number of constraints. I get one constraint. So this is A1 comma theta, and this is A1 comma L, and I only have one constraint. All right, that's what I was after. So when I'm on the theta term, I get my lambda sub k, so I only have one lambda. There's only one constraint. So I'm going to rewrite that as lambda 1 times A1 theta, which is going to be lambda. There's only one lambda, so I'll just call it lambda. You can call it lambda 1 if you want, times 0, which is just 0. And over here, AK, or lambda k times AK comma L is going to be lambda, again, my lambda 1, which is lambda A1 comma L, which is 1. So it's just lambda times 1. You see that? All right. So what I needed was, I needed the sum, actually, okay, let's go back and look at the equation. What I needed was the sum for each of these, so I'm going to do this for all j. So first we have j is equal to k. So I actually need the sum of k equals 1 to L of lambda k. No, what? Oh, yes. Yeah, that's yeah, okay. Yes, it is. Quite different, actually. It's obviously different. Okay, yes, it's a different one. Yeah, okay. Sorry about that. So here what I need is I need the sum. So maybe I can do this without messing you up too much. I needed the sum of my lambda k AK theta, because over here I'm on the theta, and over here I need the sum of my of my lambda k AKL. And I'm summing over k, so k equal 1 to a different L. Okay, it's a different L. Sorry about that. Maybe put a little star if that helps you on this example. And
now it just looks like L dot.
L dot. Okay. That doesn't help, does it? Okay, so in this case, I only have one constraint, so I just go straight to here, just one constraint. So I just get lambda 1 times A1 theta. If I had two constraints, I'd have lambda 1 plus A1 theta plus lambda 2 times A2 theta. If I had three constraints, I'd do lambda 1 plus times A1 theta plus lambda 2 times A2 theta, and so on. Okay. All right. Let's now assemble this stuff. So I get, over here, I get ML squared theta double dot plus 2ML L dot theta dot. Plus MGLS theta minus 0, lambda times 0 equals 0. And over here, I get ML double dot minus ML theta dot squared. That was the partial t with respect to theta. Minus MG cos theta. Seems like there should have been a... Yeah, minus lambda. Oh, yeah, there's a good one. All right, 1 minute warning. 1 minute warning. No. Okay, all right. 1 minute warning. What do we do now? I got that deer in the headlight look. All right, so what do we have? We've got two equations, right? We've got two unknowns in, but Drew, this is so engaging. I know you're back there saying, if only I could give him 5 more minutes. Okay, get two unknowns in Q, which are theta and L, and then we also have this extra unknown lambda, right? So that's 3 unknowns. So it's 2 unknowns in Q plus 1 unknown in lambda. So we need 3 unknowns. So we need one more equation, right? Plus 1 equation. The extra equation comes from the constraint. All right. And so let's take the constraint. The constraint was L is LC. So now we're going to apply the constraint. So we got 3 equations, 1, 2, 3, and 3 unknowns. And so we solve. Now, there is something a little odd about solving here. And I say odd, it seems a little odd to me. I'll let you decide if it's odd or not. So now I'm going to do one more step, which is I'm going to substitute in a little bit. L equals LC. What does that tell me about L dot? 0. Does it tell me about L double dot? 0. So I'm going to put that back into our other. So I'm going to go back to 2 equations. I'm going to now substitute 3 into 1 and 2. All right. When I do that, I get ML squared theta double dot. Let's see, the second term goes to 0 plus MGLS theta equals 0. So I get that equation. That's 1 modified by 3. And then 2 modified by 3. I get the ML double dot goes to 0, but I get minus ML theta dot squared minus mg cos theta minus lambda equals 0. Now I have 2 equations. Oh, and I could put in LC. I should have done that just to bring it all home. And let me, for fun, I'm just going to move lambda over. So I'm down to 2 equations. So in this case, what I've got is, I've got my equation, my variable, the thing is my dot. I get the equation all the time. I got to determine lambda, and I told you before, the neat thing about lambda is the force that enforces the constraint. Lambda enforces the constraint. Here the constraint was that L is constant. So what enforces that? Well, it's the tension. So lambda is the tension. So here by default, I've got the tension in the thing. Okay. Drew, what do you think? 3 more minutes? 3 or 4 more minutes? What do you think? You seen a sign error? Yeah. No, it's not minus. It's for the V, it's positive. For the V term, it's positive. Yeah, I didn't. When you're practicing those, decide the way you want to do it. So the Lagrangian is defined as, I know it's a little odd the way I put these together. The Lagrangian is defined as T minus V. It's the partial Lagrange, it's minus the partial Lagrangian with respect to the Q, J. And so you get a minus times a minus. So it gives you a positive V term and a minus T term. Yeah. The signs are a little tricky there. Okay. Drew's consent to give me one more quick example, last example. And I'm going to make this really fast. Hey, what are you doing, Drew? You push over? You don't even have to try. Okay, so here's what we got. Here's what we have. We've got a ball rolling on another ball, a ball rolling on a sphere, a ball rolling on sphere. Now, this is kind of a classic little problem. You know, I know that you sit around and think about it at night. You say to yourself, oh, I've got this ball and this sphere. And if I let the ball go, at what point does the ball, you know, fly off the sphere? Separate. You know, what point, what angle, for example. Now, really, actually, let me back up. Really, what we're trying to do is, well, you know, there are two things here. I got to make this quick. All right, so let Q equal, I'm going to have two. I'm going to add another term, a Z. So at what point does it fly off, or what point, you know, does a Z take some non-zero value? So I'm going to let my Q be two terms, theta and Z. I could let it equal theta and R, but here I'm adding another term, Z. Got it? So two variables. And I want to, you know, find the equations, you know, I want to write the equations of motion. And then if I also wanted to say, when does ball just leave surface, that would be as if saying, you know, when the force between ball and sphere goes to zero. That would be like saying that just the point at which that Z starts to come off. Does that make sense? But at the moment, let's just look at it as this thing. And as I'm solving the equations of motion with Q equal theta and Z. And for this problem to save us another minute, let's assume the ball is a point mass. So I don't care about the rolling constraint. If I was considering it as a rigid body, I would ask the question, does it roll with slot? Does it slide? Does it not slide? I'd have that kinematic constraint to know both the angular velocity and the slipping. In this case, we'll make it easy. All right. So that was sort of my step 0. Kevin, we'll try to work in our better step numbers now. So step 1, I'm saying, you know, Lagrange, I got a T and B. So T is going to be 1/2 m B vector dot with B. And since it's a particle, you know, I've got no 1/2 omega dot I omega since particle. Yes. Yes. Z is, okay, so yeah, let me be clear. So the ball is rolling on this sphere, constant radius, but I'm also wanting to consider the case of the ball comes off the sphere. So I'm going to add another variable, an extension of the radial length. Oh. That would be a second variable. 2. Oh. Sorry. I thought that was 1 and 2. That's why. Yeah, let me do what I'm supposed to do when I write Z, which is a little thing there. Like normal force of the ball. Oh yeah. Also, when does ball leave surface, i.e., the force between ball and sphere goes to 0? Yeah. Drew's breathing down my neck. What can I say? Well, actually, I don't want to say that. We're going to get MATLAB stuff, so I'm really watching the time. All right, so we get this, and then we get our, we need our V, and I think we can just write this one in. It's going to be mg. So what I'm going to do is, now my radius is modified by r, basically, right? So it's going to be mg r plus z times the cosine of theta. And at this point, I guess this would be my reference. Yes, yes, yeah. So I could have some, yeah, that makes sense now, Drew. So I did not make that clear a minute ago. You could. Yeah, if you did Z from the center, you just say the constraint would be Z equals R, right? If you did it an additional one, it would be Z. Yep, that would be equally fine. Good. I like that you guys are thinking that way. So I need the kinematics. So my. Yep. What are you saying? You assumed it was a point mass. So right before that, you were saying something there about the Oh, yeah, you know, I'm trying to add some stuff, and I think I'm just making it more complicated. You know, in general, the kinetic energy at the energy due to the center of mass plus the angular energy, the moment, the energy comes to angular. Those 2 terms. That term I dropped because I'm assuming the ball has, which also means it doesn't matter if I say to the ball, what's something around? It doesn't matter because the angular motion of the ball just doesn't come into play in this simplified problem. All right, so I need my position. I need my velocity, so it's going to be the ddt of some r, and now it's going to be r plus, I guess it's going to be r plus z, and I need my angular velocity, b to n, just theta dot around the b3 direction. So when I get this, I get r is constant, but I get z dot in the, I guess this thing is in the b2 direction, isn't it? I get a z dot in the b2 plus a 3 across the 2 is a -1, so minus theta dot r plus z in the b1 direction. So now I can write my t. It's 1/2 m z dot squared plus theta dot squared r plus z squared. And I already wrote my v. And you know what, Kevin, I'm going to do? I'm going to call this 1.75. I'm going to write my constraint right now. Okay. Tuck it in. What's going on with me up here? Constraint. And the constraint that I'm going to have is that the ball stays on sphere. And the ball stays on sphere means that z equals 0. I'm going to go ahead and take a differential of my constraint. So I get my terms are theta and z. So I first take the d theta of this equation times the virtual, or times d theta. Or let me just go straight to variational form. So I'm going to take the partial respect to theta. So it's going to be 0 virtual theta plus 1 times virtual z equals 0. And you know, you might say, well, that seems trivial, but that's the process. I mean, typically that's the case. It's pretty, it's just the way it works. And it's powerful. It does work out. And then I can write my matrix out. So it's 0 and 1. This looks just like the last problem, really. Virtual theta, virtual z equals 0. Now I'm ready to do my terms. So I've got q equals theta and q equals z. For q equals theta, my partial of t with respect to theta is 0. My partial of t with respect to theta dot is m theta dot r plus z squared. The ddt of this thing is m theta double dot r plus z squared. Plus, I've got to add this other term in, 2m theta dot r plus z times z dot. Partial of v with respect to theta. Looks like it's negative mgr plus z sine theta. And q of theta, 0. And finally, the sum. I'm going to do it right this time. The sum for k equal 1 to just 1. I only have one constraint, right? Of my lambda sub k, a k theta equals lambda 1 times a1 theta, which is lambda 1 times 0, which is 0. Q equals z. My partial of t with respect to z, like I'm going to get a m theta dot squared r plus z times 1. Partial of t with respect to z dot. m z dot 2, yeah, mz dot d dt of that thing, m z double dot partial of v with respect to z. I think that's mg c theta. I think it's just mg c theta. Yes, right here. Yeah. It's a z going crazy on me. There's a z trying to get away. Oh. Okay, and then finally, okay, my q sub z is 0, and the sum for k equal 1 to 1 in this case, a lambda k a z, oh no, a k z equals just lambda 1, just lambda, because we had the 1 from above. All right, put it all together. We get m theta double dot r plus z squared plus 2 m theta dot r plus z c dot minus mg r plus z sine theta equals 0. That's our first equation. That's from this guy. Our second equation is from over here. We get m c double dot minus, we have a t term, minus m theta dot squared r plus z plus mg cos theta minus lambda equals 0. So same thing as before, you know, 2 equations of motion, 3 unknowns, 2 generalized coordinates plus the lambda we've introduced. In this case, if we had more constraints, there'd be more lambdas. So we need a third equation. It's the constraint. In this case, z equals 0, which implies z dot equals z double dot, which equals 0. We'll plug 3 back into 1 and 2. I'll get m theta double dot r plus z squared minus mg r quantity r plus z sine theta equals 0, and m minus m theta dot, oh yeah, these are 0. Yep. M theta dots, yes, good. Did everyone get that? These are 0. M theta dot squared r plus mg cos theta equals lambda. So that's the force that I see, you know, that's the force on the sphere. That force acting on the sphere is 12. And then if you, again, well, when does that thing come off the surface? Well, it comes off the surface right, v doesn't go right as it comes off. We leave v equals 0 in. This is the force that, and force that contains v equals 0. That's that force compression. After it comes off. So you're going to say, well, what, then the same thing moves that force to 0, to set that equal to 0, it's also theta. So, okay. Nope. Yeah. Right here. Oh, in it, yeah. In this, it's L is 1, the number of constraints. And in this case, there's just one constraint. You know, both my examples had just one constraint. You would add more as you have more constraints.